welcome. This is the module 5, that is the 5th week, and my first lecture will be on the Borden distribution. Now, what is the takeaway from this lecture will be importance of the Borden distribution, and basically why we are bothered about the Borden distribution, and then conventional double bell charging, bell-less charging, and different type of stroke profile like V and M Borden profile. Then we will discuss about the charging sequence and the Borden monitoring device that are in place, and how Borden distribution correlate with these different measurements and can rectify the different Borden problem. So, now first is the importance of the Borden distribution. Actually, why should we bother about this Borden distribution, and what is the role of Borden distribution in the performance of blast furnace operation? And why basically this Borden distribution come into picture is due to wide variation in the physical properties of the material or the Borden raw material or the Borden of the blast furnace. Okay, wide variation in the physical properties if you consider, because first of all there is a huge size and shape distribution. As you can find the size and shape distribution, you will find that iron ore size varies from maybe 10 to 30 millimeter, where the coke size may vary from 40 to 80 millimeter, like that. So, there is a huge difference, and also there is a size distribution both in the raw material iron ore as well as coke. There is a size distribution, wide range of size distribution, as well as you have size difference. And shape also differ because sinter is become little irregular, while coke is also not very regular, and lumpy ore Borden material also not very regular. Only pellets are very spherical, that is almost spherical size pellets are there. Okay. Otherwise, the shape are not very regular. Okay. So, there is a size and shape distribution. And then you have physical property. If you consider, you have a density difference, and obviously if you consider iron ore is much heavier compared to the coke, maybe 5 times, because the specific gravity there is the density maybe 5 gram per cc for iron ore, and for coke it may be 1, and limestone in between, right. So, there is a huge density difference and coefficient of friction, both internal as well as external. What do you mean by that? Is basically when you consider a compact of material, then it is called the internal coefficient of friction. Basically, if you have a compact of material, and if you pour on a floor, ground floor, you will find they form a ridge. Okay? And this angle with the horizontal of this ridge, if you see the vertical inclined surface along which they aligned, if you take an angle, that is called the angle of repose, and that angle of repose varies from material to material, and it depends on the internal coefficient of friction. That is the how the particle, when these particles are there, what are the internal friction, depending on that they will form an angle with the horizontal. Okay. So, that varies from raw material to raw material, and especially if your raw material has wide size distribution, shape distribution, and moist, heavy, they usually try to form a ridge. Okay. So, they try to form a higher angle of repose. So, that is that coefficient of friction is important. So, that is why there is I am calling there is the angle of repose. Angle of repose is, as I said, if you take some material and put on a horizontal surface, they will make an angle, they will make a pile, okay, and that pile will have a certain angle with the horizontal, and then if I just show it like this, I can show here. We take a pin, and then suppose you put some material and it makes a heap like this, right. This is the material I have put on a surface, and then this angle, right, this angle, it is theta, or you can write it just like this, I can call it as theta. This angle, right, this angle is called the theta, or called the angle of repose. That is called the angle of repose, and that varies from material to material. For example, coke will have a little angle of repose, or the iron ore with fines, basically those who have wide distribution of fines and moist, little heavy, that is the iron ore, they will try to make a little stiffer angle. So, and that is called the natural angle of repose. And in fact, in the blast furnace, when you charge, then it is not only the natural angle of repose, because other factors like wall, vicinity of wall also influence the angle of repose, or when the material is falling, that is called the stream. When the stream of material is coming, that is also forced to change the angle of repose. Anyway, so angle of repose is very high, especially for the very fine. If you can see, that is the for fines, iron ore with fines tries to form a ridge, as I said, while the bigger and lighter particle like coke try to roll down the stroke line. So, if you fall coke somewhere, they will try to roll down that is the ridge, and iron ore along with fines, they will try to form a ridge. Okay. So, that is there. So, as a result, you can see the difference of angle of repose to different materials. So, different material after falling into the stroke line, they behave differently. They either may roll down, or they may try to stick to the location where they are fall, at the point of fall. So, as a result, you can expect a lot of segregation can happen. So, and it is a very important parameter, as you will see, that is the ore to coke ratio. Ore to coke ratio is a very important parameter, where the ore to coke ratio is high, it is likely to be offer more resistance to the gas flow compared to the place where the ore to coke ratio is less. That is, the amount of coke is more, because the coke is more permeable. They find the paths for the gas passage. Okay. So, that is very important, ore to coke ratio. And because the ores, where there is ore, there is the likely chances of fines are there, and then the gas resistance is more, because the pores are not sufficient. Where the coke is there, the more bed is more permeable, you can expect more gas to pass through. Okay. And after that, let us come to the conventional double bill charging. That is the importance just I have talked about, because since there is a huge difference in physical properties and size, shape, distribution, basically if you just charge arbitrarily, then it is not likely you will can get an uniform, what is that, what I want to tell, just I am going back to that. So, you won't get a uniform distribution of permeability, bed permeability across the radial cross section. So, you have to have a perfect charging system that will try to maintain a uniform permeability across the radial section, although it is not possible to make it complete uniform, but you can move towards that. But if you charge arbitrarily, it is not possible. So, how will you charge the material, and which sequence, and where you want to fall iron ore, coke, the point of fall and the sequence, these are very important to maintain the burden distribution, to maintain the uniform permeability, more or less close to the uniform. But it is not possible, I am telling that, to get a perfect uniform permeability in a blast furnace, because there are a lot of segregation stations, even in the distributor, that is the from where the burdens are coming, they also generate some segregation when they fall, then also you generate segregation. So, anyway, this segregation you cannot avoid, but you can limit those to a very large extent. So, as a result, you can have more uniform permeability. Now, anyway, let us see what are the charging system in store for us. There are basically two charging systems are there. One is very conventional, called the double bell charging. You have two bells. One is called the upper bell, there is the upper or lower bell, and this is the upper bell, small bell. This is comparatively small, you can find, and another bell is there. This is called the big bell, that is comparatively bigger, and you can independently control the movement of the lower and the upper bell, right. So, initially what happens, both the bells are closed, and that is both the bells remain closed when charge loading over the small bed. When you are charging, that is when the charge is loading. Charge means burden charge, that is being loaded on the small bell. You can find this is the portion when there is the skip car are coming. Skip car will come from here. There is the skip car. They are putting the material over the small bell. So, on small bell, everything is closing, all the material is getting dumped here now. And the next cycle you can find what is happening. You can find that is now the large bell remain closed when the small bell open to admit the charge over the large bell. Basically, here your large bell is remain closed and small bell is lowered little. If you just lower it, then it will give the passage for the material to flow from the small base over the small bell over the large bell. You can see from here the material is loading over the large bell and the small bell has been lowered. So, now during this period this large bell still remain closed, since as a result your gas, blast furnace gas, cannot pass through this charging location, otherwise it will pass and go to the atmosphere, pollute the atmosphere. So, that is why this is the system by which you can keep the blast furnace gas not to pass through these charging devices, okay, and go get open to the. And what happens is that you have to there is the gate valve is there, that is you have the gas taker, off taker, through which the gas can only pass. So, they cannot pass through this thing. So, now, so all the material has been charged. In the next cycle you can find now the big bell is lowered. If the big bell is lowered, then your small bell is closed. Now, small bell has been closed such that the gas cannot escape because the big bell has been lowered. So, material is coming down, some amount of the gas can come and then go away. That is why the small bell is also taken off such that it closed the door here. Okay. Now, the material is coming now from, finally it is charging on the stock line. The material is coming from the big bell and it is charging on the stock line and making a profile. Okay, so now in this case what happens? Now you can find that both the bells has been taken off and both are closed and you can repeat the process. So that is the way material is charged, first on the small bell, then on the big bell, and then the big bell lowers and the material is admitted over the stock. And in any process, in this process, and at that is you keep action such that, or keep measures such that the gas cannot pass through it. So, you alternately open and close the big bell and the small bell. Okay, so this is the way it operates. Now, development in the charging system, if you see, initially we have only bell charging, and in the bell charging what happens, when the big bell lowers, the material comes and the material will fall like this and come here. It will strike, basically material will strike the, what is that called, that is the furnace wall, that is the stack wall, okay, and then they will be deflected back here like that, or depending on. So, the material will come and it will just, so such that the material, if they heat the wall also, then the problem is the wall will, refractory will erode quickly, that is there will be some friction and then, okay, so erosion of the refractory wall can be there. That is why you have the movable armor. It has two purposes basically. One thing is that to protect the refractory, and second thing is that it can move in this way. It can move up and back, right, this. So, it can move in this direction as well as this direction. So, when it is moving up, basically the material will hit it and will be deflected more near the center, and when it is in the lower position, that is the down position, this is the, I am calling it, that is your, I will just call it like this. So, this armor can move this way. So, when the armor has come in this position, suppose this is the position it has come, so then the material, suppose it is coming, it will be deflected here. So, if another color I can take, if it is possible, let us see, and if it comes here, then it can be deflected little up. So, the material can be pushed more near the center if you just push the armor inside the furnace, more inside the furnace, then it can push the material more towards the center of the blast furnace rather than, otherwise it will be this way. So, by moving the armor back and forth, you can charge the material in any cross section, not any cross section, you have something, you can put the material more towards the axis, central axis, or towards the periphery, right, or the near the wall. So, depending on that, where is the position, you can have some control, but you have some control to deflect the material towards the axis or towards the periphery, right. So, this is the way it works. That is the only control we have. Through the movable throat armor, we have the control. Now, then came the bell-less charging, that is the middle, you can say these two are called the bell-less charging, both are called the bell-less charging. So, in this case you can find a rotating chute is there, this can rotate basically it can rotate, interestingly it can rotate in any angle, okay. So it just rotate through 180 degree, that is the 360 degree it can rotate, and it can be up and down also. You can move it up and down. This motion, these two motions are there. It can be lifted up and then like this. So it can move like this, or it can up and then move like this. So as a result, you can access different concentric circles. So as a result, what you can access different concentric circles like this in the blast furnace. You can feed the material in any of the concentric circles. So that is the advantage of the chute system. That is the bell-less top. It is called the bell-less top because you do not have any bell. You have a rotating chute, basically that distributes the material. And here basically you have the hopper. You can find there is a hopper through which the material first from the skip car, it comes to the hopper. It is a storage place of material, and then the material comes through it, delivered to the chute, and then finally chute distribute the material along any concentric circle where you want to put it. So you have much more better control to put the material where you want to put it. There is any concentric circle, and near the very axis and near the periphery, anywhere you can put, and it is usually number 1, 2, 3, 4, 7, 8, like this, 7, 8 concentric circle. 8 basically higher number represent near the periphery, lower number represent towards the center. So 1 means you are just putting the material in the center, 8 means you are putting the material along the periphery. So that is there. Now next development is there. This is called the bell-less top. You have more control of distributing the material, and then you have a 2 bunker. Basically you have 2 bunker, and then material is coming, and then you are doing the same thing. But in this case, what happens when you have a 2 bunker, you can charge 1 bunker while you can empty the next bunker. As a result, the process becomes very continuous. You can continuously put the material, because one bunker will be on charge, another will be releasing the material towards the chute and from the chute to the stock line. So it is a more continuous process rather than this single. It has some problem basically, because when you are charging and then when gas basically here, there is the controlling the top pressure, okay, at the top, because with this also, with this system, you are maintaining a high top pressure at the blast furnace top was much more easier, and with the 2 bunker it becomes much more easier, because one on charging, one on loading the chute. So that way it is better, and here control was little less. That's why there is a development. Okay. So now we have talked about this bell-less charging. Now we go to, there is stroke profile. Basically, what type of stroke profile we have? I said there are 2 kinds of stroke profile. One is called the V profile, and this is called the M profile. And when these stroke profiler forms, you can see with the bell-less charging, basically it was, if you charge the material near the wall, this is in case of the bell charging, if your armor location is towards the periphery, because then it will not deflect the material too much, the material will fall near the wall, and then what happens, there is the fines from a ridge near the wall, because obviously you have ore material, you have lot of fines with it. Some fines you cannot because of impact also. If the original raw material do not have fines also, some fines are there, because there is the distribution, basically 5 millimeter onward you charge. So 5 to 20 millimeter like that. So if you are charging it, so you have some fines, already some fines will be generated during the impact and all these things. So fines, or every iron ore contains a lot of fines along with it, it will have some fines. So those fines will try to form a ridge near the wall. And as I said, there is the moist ore and all these things, they do not have much very steep angle of repose. So they will try to stick to the place where they are falling, especially the fines. And the bigger iron ore can roll down to some extent, but the fines will try to form a ridge. And then this is the thing. So your material is coming, it is just charging the wall. There is maybe the armor is there because it is charging near the wall. So it will be depositing. There is the fines will not move. Here it will fall, and all the fines will be there. And the coke, iron ore to some extent will be rolled down towards the center. So finally, you can have this type of distribution. More coke you can find here, and the iron ore is more near the periphery, and it is slowly decreasing towards the center. At the center itself, maybe some location where only coke. So this is the ore distribution, this is the coke distribution. So you can find that is coke roll down towards the axis, as I said, and some iron ore also rolling down. That's why they are coming here, because everything is dumped here at the wall, So fines, iron ore fines are remaining here only, bigger iron ore also rolling down to some extent, but the coke are lighter and bigger, and they basically roll down much more distance. So they are coming here. So this is the profile you can get. And if you see the ore coke ratio, obviously it is minimum at the center because ore almost very less here. Coke is majority, so ore coke ratio is minimum and ore coke ratio is maximum near the wall. So you can find this is more, it will offer much less resistance to the gas flow. So gas will prefer to flow through this coke region, and this region gas resistance is more. But anyway, that is the here at the near the center, the gas flow will be much less compared to that of the in this region. Okay. So as a result, what happens? The permeability of the bed increases towards the center, obviously, as you can know, and the burden distance become difficult. Here, burden descent because you are accumulating the fines near the wall, right? And as a result, so since there is a fine accumulation, if fines accumulation, the coefficient of friction will be higher because fines give more resistance to the movement. Okay, so as a result, across the wall, it will be difficult for the burden material to come down because of lot of resistance due to friction because of fine generation. So burden descent become little difficult because the gas flow, if there is a gas flow, the gas also sometimes acts as a lubricant. But since the gas flow will be very minimal because of very fine accumulation and the resistance to gas flow will be high, so gas cannot also pass through significantly through the periphery. As a result, it cannot act as a lubricant. As a result, and all the solid are there, and then they will offer a lot of resistance, the burden cannot move smoothly. Chances of accretion formation is also there because if the heat transfer will also be little less, because if you have fine accumulation, they will not allow the heat to pass through it, rather it will be accumulated into this solid. As a result, temperature will increase, and then fine also can fuse to some extent, especially it can form the slags and all this thing, and then can form the accretion also, and that is called the scab formation. And this scab is also not good. Sometimes the resistance becomes so much that the material cannot move, and suddenly when the overburden become high, the scab can break, or all the different temperature condition also the scab can melt, and then when the material can suddenly fall below the furnace, and that will be also a thermal imbalance. Okay. So those chances are there. Now, this is the bad thing of the V profile. Now we have another profile that is called the M profile, and that is a much better profile of blast furnace burden distribution. And here basically charge, material burden or charge away from the wall, not from at the wall, because at the wall if you feel, then all the problems that is coming. So ridge will also form away from the wall. Obviously, at the point of fall, all the fines will form a ridge. Okay, so ridge is forming now near away from the wall, right? So you have this type of profile because the material is falling here. You have a movable armor here, so armor is deflecting the material away from the wall. So here the material is coming in this location. So in this location, the ridge is forming, and whatever the coke fall here, coke will roll down here and here. In both this direction, coke can roll, and iron ore also to some extent will move this direction and this direction. But fines will form a ridge here. So you get some profile which looks like a M. That's why this is called the M profile, right? As I said, right, and ore coke ratio, if you can find also in this case, ore coke ratio will be low here, as well as at the periphery also ore coke ratio will be little lower because coal has to some extent rolled down here also. So you have some coke here also. Here also you have coke. So more coke here as well as here. So as a result, ore coke ratio is low near the periphery as well as the center, and ore coke ratio is maximum near this region, that is the ridge region, obviously. So now what happens, since the ore coke, so permeability, now you have a permeability both near the periphery as well as near the central region. Obviously it is more permeable, but still the periphery is now loosened because of coke is there, and it is more permeable also. So gas will flow both peripherally as well as central flow. Central and peripheral flow will be there. That is the most desired thing. You cannot, most ideal situation, if the gas flows uniformly across the cross section, but it is not possible. So, but you can see there is the majority of the porphyry and the central regions are very permeable, only ridge region is little less permeable. So, that is okay. So, that is why this profile is much better profile, because you have both central as well as peripheral flow. And burden descent now is smooth, because as I said, since the gas will be able to move across the periphery, it will act as a lubricant. So, the burden will smoothly fall down. Besides, the fines are also not much now near the wall. So, burden will smoothly come down, scap formation will be less and all these things. But because of sometimes what happens, some accretion also can form, because the larger gas flow, if it is the gas flow is very large, then also it's sometimes difficult, because too much of gas flow means gas is the hot gas that will move. So, as a result, you are bringing hot, there is a temperature, there is a heat by convection also near the wall. Okay. In here you are bringing the heat by convection near the wall. As a result, what will happen? Heat accumulation will be there. There are obviously some fines, so they will also can form some accretion. So, you have to keep in mind, if you make the periphery too much permeable, that is also not good. So, that way you have to make the charging sequence, you have to control how much coke you will fall and where. So, that is there. So, too much of peripheral permeability is not good also. Too much of gas flow can form some accretion. It is reverse way here, because the heat is coming by convection, and some fines will also be there, and also because of high heat, if you have heat is more, then fusion can take place. So, as a result, the accretion formation chances are there. Okay. Otherwise, the M profile is very good. Now, the bell-less charging. Now, what is this bell-less charging? As I said, you can find it is the most modern one. 2 hopper system is there, and then the material is coming from this hopper, and then the material is coming from this hopper also, and they are coming to a cylindrical portion, then coming to the chute, and finally they get distributed. Okay. Some distribution is there. Okay. So, this is the way, it is nothing but you can show pictorial form is like this. So, material can be charged in the concentric circle, as I just said, and also the charging may be controlled in real time based on the pressure data under the underburden. You have lot of underburden probes in the blast furnace. So, if you can monitor the pressure drop, local pressure distribution and the pressure drop, as I said, and according to that, you can make the charging. You can, if some region is very impervious, you can attempt to charge some more coke in that location, such that it becomes little permeable. So, by taking a real-time input from the underburden probes, you can control the burden distribution, and control of burden distribution is easy now, because chute can place the coke any location you want to know. So, if some very permeable region is there, you can put some amount of ore there. If there is some very impervious region, you can put some amount of coke there. So, that type of control is possible. Now, sources of segregation, as I said, segregation not only take place at the stock line, because the segregation is taking in the distributor itself. If you consider the hopper of the bell-less charging, just the hopper that I showed, there also some segregation take place. How does? There is a fines will try to along the feeding line, because when the material is coming down through a bunker, when the material is coming down like this. So, the material will coming down like this. So, you have this type of velocity profile. So, this is the velocity profile, and all the fines will be dragged here, fines will be dragged near the quartz, and the quartz particle will be here, COARAC. The quartz particle will align along the wall, where the fines will be dragged near the central line. So, you can find, that's as a fine along, that is the fines align along the feeding and the quartz along the wall, and discharging core draws the fines fast. As a result, when you are discharging, it will be the fine will come fast than the quartz. So, some segregation is taking place in the hopper itself. So, then you can find there is a segregation called the chute segregation, because when the material is coming over the falling on the chute, then also you can have some kind of segregation developed, because quartz and lighter particle ride up the chute, because chute is like this, it is also your cylindrical thing. So, if you can see it, it is a cylindrical sheet. So, what happens in this chute also, that is the coarse and the lighter particle, it is a rectangular channel, no? In the chute, it is a rectangular channel. So, what happens, coarse and lighter particle ride up the chute, light up the chute, and the fines and dense will remain at the bottom of the chute. So, as a result, when this material is coming, so when they will free fall, then also it will make a segregation. Already segregation is taking place over the chute also. There is the fines and dense at the bottom, and the lighter and the coarser particle are at the up. So, you can find there is also a, and then you have steam segregation. There is something is called the steam segregation also, because what happens, the steam segregation, if I say, steam segregation means when the material is falling, they will fall like this. That is the thing, that is the way, because the heavier and the heavier particle will come here, coarse and lighter, like the coarse and lighter will follow this, where heavy and regular shape they will follow. You can find that is when they are coming out of the chute, they will also, because the coarse and lighter will be on the top. So, they will fall on the stock line when they are falling. There is the coarse and lighter will come here, and the fine, there is the heavy and the regular particle will come here. So, their fall, the point of fall will also be different because of steam segregation is there. Because when the material is coming, they will also be segregated. Heavier will be below, and the coarse and lighter will be on the top. So, the coke will fall from the chute, coke will fall here, where the pellets and the heavy iron ore will fall in this region. So, that will make a segregation. And there is some kind of other kind of segregation that is called the collapse also. And then, so sometimes something is called the coke collapse. Coke collapse is what? That is, you have a periphery like this. That is the M profile, whatever you draw, and then, right, and suppose you have some amount of coke is here, this is the coke, and here already coke is there, that is, you have coke only here, okay, you have some amount of coke here also. So, what happens, this coke can collapse also. This coke from here, sometimes the coke can collapse and come in the center region. When it happens, if the angle of, that is the angle of cochlear inclination, if this cochlear inclination in this time, because of gravity, okay, cochlear inclination is greater than the angle of internal friction, because coke has some internal friction, but if the angle they are shedding towards the, so if the gravity sometimes, if the gravity is become greater than that, the friction, then this material will fall. That is called the coke collapse also. As a result, it also leads to the segregation. Besides, you have the fine particle, they percolate through the coarse particle. So, there are several opportunities of the ore segregation, ore and coke segregation into the stock line. So, it is unlikely, very unlikely that you will have a uniform permeability, but you can control this as much as possible. So, now we will talk about little bit of the charging sequence, that is the burden distribution you are charging. Charging means, charging sequence refers to the things where how you are charging the ore, coke and the limestone. Okay. So, charging sequence, when I say there is the OOLCC, what does it mean? O stands for ore, L stands for limestone, C stands for coke. So, we first give 2 skip of iron ore, followed by 1 skip of lime and then 2 skip of carbon. This is there in the bell. When the bell is lowered, all this material will come down. So, what will come down first? That is the ore will come down first, 2 skip of ore will come, and then lime will come, and then the coke will come. Now, if it is the charging sequence, then what you get, that ore at the periphery, okay, ore at periphery and coke goes to the axis. In this case, the ore goes to the periphery and the coke goes to the axis, and this filling is desirable if the amount of fines is less, because when you are giving the ore near the periphery, fines is more, then it will form a V type of profile, and ridge formation will be at the wall. That is not good, that we have said. Okay, so if fines is less, then we will prefer this type of sequence. And a lower coke rate is usually because of better peripheral utilization of CO, because if you do not have much of fines, then the periphery will also be that is your permeable, and you can have more flow of the CO and the better utilization of the CO, because CO will move and ore is there. Okay. And reverse cycle is there, you can have triple C double O L, and this you just change the reverse. First you charge the coke and then the ore, then the limestone. When you do that, basically in this case what happens, ore will rolls to the center, loosening the periphery, because ore is there, because first you charge the coke and then ore, and then ore basically roll down towards the center and loosening the periphery. And this filling mix the inner wall hotter. Sometimes it may make inner wall hotter because the ore coke ratio is very low near the periphery. That is also not good. It is very low because you have charged only the coke near the periphery, and then you charge the ore will roll down to the center. So in this case, the periphery become, there's the ore to coke ratio become low, so only the gas pass through it. Okay, but not, it doesn't participate much into the reaction, and besides the coke has a very low heat capacity. As a result, temperature increases there. So that may lead to, that is the point, and results in higher coke rate, that is the inferior utilization of the CO gas, because you do not have much of ore there. And then you have a mixed filling you can have. In this case, you can charge ore and then coke and the ore and the limestone and then coke. Like this is the mixed way you can charge it. And it is suitable for ores and sinter having lot of fines. If you have lot of fines, then you use a mixed thing. Then what happens, it helps the distribution of ore and coal both in the periphery as well as the center. And the sum of the fines also roll down along with the coke. Okay, this type of mixed charging is used basically if you have lot of fines. And you have another charging technique that is called the separate filling. Here what you do, your charging sequence is first you charge the ore and then coal. So first when you lower the bell, only ore will come, and the next charging you do all the coke. So that is the way. The slash means different charging. First you charge the ore and then the coke. So it helps loosening the periphery. And this filling is very suitable for closely graded material, because this type of charging, if you do, is basically promotes the segregation. Only ore and then coke, because you have wide distribution of ore. So smaller ore will percolate through the bigger holes of the bigger ore particles, like this. So if you don't have too much of graded, that is, you have a wide distribution of size of the ores, say, in that case, there is the fines will percolate through the bigger ores, and then there's a mixed layer it will form. Segregation will be much more. So this basically allows more of segregation. Now I will talk about the sensitivity of charging position on the ore coke ratio, especially with the bell-less charging. You can see that, as I said, you can add the coke and ore at different concentric circle. Here basically I am giving 3 skew of coke at the 7th position. Basically as I say, number increases means you are charging near the periphery, number decreases means you are charging near the center. So 7 means it is near the periphery, 3 skew of carbon in the periphery, and then 1 skew at the 6th location, and another ore at the 8th location is further in the periphery, and then 2 skew of. Now this is one charging has been done, and now second charging, what I am doing in the second charging, first I have given the coke in the 8th location, then the coke in the 6th location, and the sinter in the 7th location. So if I do this way, then I can get a center ore to coke ratio 1.69, periphery 3.24, and I am just slightly changing this charging sequence, and you can find that is that the center ore coke ratio can be 0.91. It may be 0 also, and it is 0.026, and in the periphery 2.75, 2.5 to 4.75. So there is a large distribution of the ore to coke ratio, because ore to coke ratio is higher the ore to coke ratio, it becomes little impervious, but at the same time, because if your ore is there, gas will be utilized more. So ore-coke ratio should be moderate across the cross section. It should not be 0 and 2.52. 1.693, 0.24 is okay, but this is not a good situation. And you can see the charging sequence is not very changed. So it is very difficult to maintain this ore-coke ratio across this. It is very sensitive to the charging sequence also. And so more precise control of the charging has to be there. Now, I will talk about the monitoring of the burden distribution in the blast furnace. What are the, because you have to monitor the burden distribution. How do you monitor the burden distribution? Because you cannot see basically. You can monitor by in terms of heat flux, in terms of pressure distribution, in terms of temperature, in terms of surface profile, right? And for this, all types of underburden probes are there. You can measure the heat flux, okay? So at different zones, right, both above and under the burden, and the profilometers is there to measurement of the surface profile, and thermocouples are there to measure the temperature at throat, stack, and boss regions, and stack pressure monitoring and the pressure drop measurement systems are there. So underburden probes are there at regular interval in the axial direction, as well as it probes towards the radial direction also. So you can have a 3D, basically 2D distribution of pressure at different radial location and the axial location. Okay. So you have radial and axial pressure distribution is there across the blast furnace. And then spatial instruments such as infrared probes are there to monitor the burden surface temperature. And then you can measure the individual layer thickness and local descent rate, and a Tweer probe to sample materials at the Tweer levels, that is also there. Tweer probes are also there. So you can measure the Tweer probe, basically the PCI injection and all these things, those probes are very helpful to measure the, and then you have mathematical models of charge distribution control, okay, those models are there. So this model and measurement and real time controlling the burden distribution can make an ecosystem, right? So whatever, suppose you have at a certain time you have a three-dimensional pressure distribution and the pressure drop. So you can know which region is becoming impervious. If some certain region is becoming impervious, then you can add some amount of the coke at that location, because with the bell-less charging you can charge any location in a concentric circle. So if some region is impervious, you can charge some amount of coke. If some region ore-coke ratio is very low, you can charge some amount of ore there. So that way you can control the real time, you can control the burden distribution by taking the response or signal from the blast furnace in terms of different like pressure measurement, pressure drop measurement, all these things you can take as a signal as an health of the blast furnace, aerodynamics health of the blast furnace, and accordingly you can charge the burden material at different location where you want. So this type of real-time control is there, because blast furnace is a very dynamic, especially the aerodynamics thing is very dynamic, and the permeability, evolution of the permeability is very dynamic, because when the burden material is coming down, it is undergoing abrasion, impact, and all these things. As a result, fines are generated. So local condition is changing all the time. Local permeability is changing. As a result, local aerodynamics is changing. So as a result, you have to take a real-time control on charge distribution by bell-less charging. And now bell-less charging is very versatile. That's why you can do that thing. And as we have said, it is not very easy to control the segregation in the blast furnace. It will happen, because your original material are different in physical properties, as well as they undergo fine generation, degradation as they come down the blast furnace. So it is a very complex system. Now this is the conclusion. First is that we said that burden distribution is required. As I said, you have wide physical property are different for the different burden materials. So you have to have a proper burden distribution, just now I said. And burden distribution just plays a crucial role in controlling the gas flow in the blast furnace. And then there are two major stroke profile in the blast furnace, V profile and M profile. And I said the M profile is much better, because it allows both the peripheral as well as your central flow in the blast furnace. And then and a very uniform system is very difficult to generate. And removing the stock line segregation is difficult because the segregation starts in the distributed system. When you are distributing, the segregation starts from there, and in the stock lines also this segregation continues. So removing the stock line segregation is very impossible. Okay, it will happen, but you can control it. And with the most modern bell charging, it is possible for the real-time control of the bed permeability. Based on pressure drop data from underlying probe, you can get the pressure drop data from underlying probes, and you can control the burden distribution. Okay. So, as we have just discussed. So, this is the conclusion, major conclusion, and thank you very much.